Hello again. So this time we want to talk about the domain of the radical function. Okay. So like last time, I'm asking you. So what does the radical means? Usually the radical function means the inverse function of the polynomial function. So one example, if your so let's say fx equal to x squared, okay? Then we can define f inverse x becomes square root of x, but it usually plus and minus here. Okay? But now, when you do plus and minus, it's not a function. You know what I'm talking about? Okay, anyway. So the reason is, the x squared graph like this, and then you are doing inverse function based on this x or y equal to x graph here. Then this graph becomes this direction. So of course, as you see, when you draw the vertical line, it intersects more than one point, so it's not a function. That's the reason, whenever we talk about the radical function case, we always choose the side here, such as just root x or negative root x usually. Okay, so in this case, I'm going to focus on only positive side. So I'm going to just delete this one. Then I can delete this one too, right? Okay, then now finally it becomes the function here. Okay. So therefore, when you guys always look at the radical function case, it shows that just the root to x, not plus and minus root to x here. Okay. Now think about x squared domain range first. Okay. So x squared domain case, as you see, all real numbers, right? Why? Because you see the graph on the left side and also right side. Therefore, domain become all real numbers. Then what about the range? So y value must be bigger than or equal to 0. Okay? Why? Because you don't see any curve under the x-axis. That's the reason we can define range become y is bigger than or equal to 0 here. Now, we said that this is the inverse function of x squared function, right? Then, this one, domain must reflect y equal to x squared to the range value here, okay? So therefore, this function case, domain becomes x must be positive or equal to 0. But in the range, it become all real numbers. Okay? But anyway, so we just focus on domain this video. So after this, when I give you some example, I'm not gonna find the range, but the reason I explain this way so that we can define, why, the y equal to root x graph always domain is limited and the range is all real number. That's the reason. Okay. So now, one more example before I'm gonna bring out other cases here. So let's say gx equal to cubic, I meant x cube, okay? So x cube. So you know the x cube graph becomes this way, right? So how to determine domain for y equal to x cube graph? So as you see, this is all real numbers. The same way, range also y or real numbers. Then now we can define inverse of gx function become cubic root x. Then now this one graph must be so this way and this way, and then so domain equal to x or real numbers, and the range also y or real numbers. So far so good? Okay, I have a reason to show these two different scenarios here. Okay, so when you look at those two cases, so x squared case is like an even degree case, x cubed means odd degree case. And then interestingly, when you find out y equal to x fourth or y equal to x sixth, all these graphs, even though their stiffness may be different, but they're all similar to y equal to x squared graph. Looks like this. If this is the x squared graph, then y fourth becomes a little bit like this, and then something like that, and then I can see y x sixth means more like this. So even though shapes are a little bit different based on stiffness, but domain and range, all these even degree power show exactly the same. Okay? Therefore, in the inverse function, any y equal to n root x, this case n is even, then the domain is always limited. Like this. Okay? However, odd case, the y equal to x fifth, y equal to x seventh, something like that, the same scenario basically. So if x cubed is like this, then x fifth become sum out like this, and x7 become even more, something like that. Okay, so this odd function case, domain and range both cover all real number basically. Okay, so this case domain is all real numbers basically. Okay, so I'm gonna say range also y or real numbers. Make sense? Okay. Then now, so this kind of basic, fundamental function form, we need to find their domain value. But the key point is, what if the function form is a little bit more difficult, such as, just a fx equal to maybe square root 2x minus 5 here. Okay, then now, the first thing you have to watch first, which is this number here. No number means square. Square means even. Even means this inside value must be bigger than 0 or equal to 0. Am I making sense? Yeah. So this case, domain, you have to set up. So I'm going to set up 2x minus 5 is bigger than or equal to 0. So plus 5. So 2x is bigger than or equal to 5 divided by 2. So x is bigger than or equal to 5 over 2. So you can determine this case, domain x is bigger than or equal to 5 over 2. Okay? So what about the given gx? I'm gonna say square root maybe, so 5x minus 4. Same thing. I meant fourth root actually, fourth root. So fourth root also even, so you can just say 5x minus 4 must be bigger than 0, and then plus 4, then 5x is bigger than or equal to 4, and divide by 5, then domain becomes x must be bigger than or equal to 4 over 5. How simple it is, right? Okay, then what about the odd case? So sometimes you may get such as gx equal to cubic root 2x plus 1, something like that. It is cubic. Cubic covers every number. What does that mean? Then no matter what, you see odd here, so you conclude that domain becomes all real values. Am I making sense? Again, why I choose all real value for cubic root 2x plus 1? Because cubic case, it covers both positive direction, also negative direction. That's why you can say domain become all real value here. Okay, one more. I'm gonna give you hx equal to maybe 7th root 3x. What do you think? It is odd. Odd means all real value. So domain becomes all real value basically. Make sense? Okay, so that's all this video, and then I'm gonna bring out the little bit more complicated example of determine domain for radical function for the next video. Okay, thank you.